We use vectors all the time in math, physics, and animation to represent change or motion that has both a magnitude and a direction. But have you ever multiplied two vectors? Here we'll see how to multiply vectors, understand the connection between vectors and complex numbers, and see how so-called imaginary numbers have some important real-world uses in modeling motion. Before we get into multiplying vectors, let's think about adding them. It's pretty common to add two vectors. If I walk 3 meters in this direction, then 4 meters in that direction, the result is the same as if I had walked about 5 meters in this resulting direction. You can find the result of adding two vectors by adding their x and y components. But what does it mean to multiply two vectors? Let's check out two methods. Method 1, logarithms. To find the product of two numbers a and b, you can either multiply them, a times b, or take the log of each number, add the logs, and then exponentiate. That's actually the defining property of logarithms. Log of a times b is equal to the log of a plus the log of b. To multiply two vectors, we just need to know what the log of a vector is, then add the logs. But what is the log of a vector? For these two-dimensional unit-length vectors, believe it or not, the log is just the angle the vector makes with the x-axis. To see this in action, take this vector a that lies along the x-axis. It makes a 0-degree angle with the x-axis, so its log is 0. If we were to multiply this vector by some other vector b, then that means we add its log. We add 0, so nothing changes. Now if we move a to be at a 45-degree angle, then multiplying a and b results in a new vector c that is 45 degrees past b. Multiplying unit-length vectors means adding their angles. If the vectors are not unit length, the length of the resultant vector will be the product of the lengths of the vectors that went into the multiplication. So if we make b twice as long, then the result of a times b will be twice as long as well. Before moving on, let's try one more example. Coming back to the vector of length 1, pointing up the y-axis, let's rename it I. What do we get when we multiply this vector by itself? What's I squared? Well, I is 90 degrees from the x-axis, so multiplying I by I means adding another 90 degrees of rotation, leading to this resulting vector pointing left. So I squared is the vector pointing at -1. Hopefully this example starts you thinking about method 2, imaginary numbers. So far we've been thinking about vectors living in graphs with an x and y axis, but we can instead think about graphing imaginary numbers. Now the x-axis will become our number line. We can think about the points 1, 2, -1.5 as points on this number line, with negative numbers as points to the left of the origin. The y-axis can serve as a second number line that allows us to create perpendicular numbers. These perpendicular numbers are what's more commonly referred to as imaginary numbers, and we'll use I to denote whether a number is imaginary. So here is where the perpendicular number 1 is located at imaginary 1 or 1i. Likewise, here is imaginary 2 and imaginary -1.5. We can also mix and match to create complex numbers with both a real and an imaginary part. Here is 1 plus 2i and 1/2 minus 1i. If we want to add complex numbers, we can add the real and imaginary components separately, just like vectors. So 1 plus 2 imaginary added to 1/2 minus 1 imaginary gives 1.5 plus 1 imaginary. To multiply imaginary numbers, we need to do some algebra. We have a plus bi times c plus di. We can use the distributive property to get a times c plus di plus bi times c plus di, which is ac plus adi plus bci plus bdi times I. With imaginary numbers, I times I squared, is defined to be -1, leading to ac plus adi plus bci minus bd. Or, gathering like terms, AC minus BD is the real part, and AD plus BC is the imaginary part of the resulting multiplication. Applying this simple algebraic rule lets us multiply any 2 points. For example, 1 plus 2i times 1 minus I becomes this, which simplifies to 1 plus 2 plus -1 plus 2i, or 3 plus I. The code for implementing complex numbers is of course straightforward. We can initialize both the real and imaginary part of the complex number. Then adding is just making a new number with the corresponding real and imaginary parts added to each other. And multiplying is creating a new number following the algebraic rule of multiplication that we just derived. Let's compact the code a little bit and use it to verify the multiplication we did by hand. We can define a and b as the two complex numbers and multiply them with our code. And we can see that the result is a complex number with the real part of 3 and an imaginary part of 1, matching our result by hand of 3 plus I. So what does this have to do with vectors? Well, a 2D vector can be thought of as an imaginary number with the x component being the real value and the y component being the imaginary value. So 1 plus 2i is a vector with an x value of 1 and a y value of 2. And 1 minus I is a vector with an x value of 1 and a y value of negative 1. So we can multiply vectors by first interpreting them as complex numbers and then multiplying the resulting complex numbers. Going back to our example of a vector of length 1 pointing straight up, this is 0 plus 1i. What do we get when we multiply this vector by itself? Well, 1i times 1i is negative 1. That's exactly the definition of an imaginary number. So the resulting vector is negative 1 in the real axis and 0 in the imaginary axis. As you've probably realized, both methods give the same result. This is because the angle of the corresponding vector can be viewed as the imaginary logarithm of the complex number. If you've seen the polar representation of imaginary numbers before, this shouldn't be so much of a surprise to you. Understanding that complex numbers can both be 2D vectors and represent transformation to 2D vectors helps a lot in understanding their uses. In computer graphics, video games, and virtual reality, we often have a character that can move across the screen, tilt or rotate. We can view the location of our character as a complex number. Then moving the character along the screen becomes adding vectors, and rotating the character is vector multiplication. And we can do both at the same time to create interesting animations. As much as I love complex numbers, there are alternatives and limitations to consider. A complex number a plus bi can be represented as a matrix a minus b, ba, which is extremely common in computer graphics. But this actually takes up a little bit more memory or storage than working with complex numbers directly, which can sometimes be a problem for some applications. A key limitation, though, is complex numbers can only represent 1 degree of rotation, which is all you have in 2D. So spinning a flat wheel using complex numbers is great. But what if you're working with a 3D object? They can rotate in 3 ways. They can roll along their central axis, they can pitch down or up, and they can yaw to change their heading left or right. This limitation comes from the fact that complex numbers only have one imaginary axis, I, so they can only represent 1 degree of rotation. We need something with more power. Quaternions are imaginary numbers, but upgraded with 3 different imaginary axes, I, j, and k, allowing them to represent rotation in any of the 3 dimensions. Understanding quaternions is vital for studying anything that moves in 3D, including the fields of computer graphics, physics, aerospace, and robotics. But quaternions deserve to be their own topic, so we'll have to cover them when I see you in a future video.